Okay. This week, but I mean, it's actually have a fair amount to cover, both days, so. Thursday especially, very important, please be on time. Right. Okay, we'll see how this goes. All right. So we've seen various time-stepping methods, one-step methods such as Rowan-Counter methods, also multi-step methods. Our focus today is on stability, whatever time-stepping methods you have. Okay. Big problem for time-stepping methods. Okay. So suppose you have your PDE and then you spatially discretize it and you wind up with a system of ODEs, considered a linear case. Y prime equals AY. With initial condition. So we know what the exact solution is. EVAT, why not? The trouble is, for a system of ODEs that comes from a PDE, the matrix A is generally large, ill-conditioned, so computing the actual matrix exponential is generally not practical. Well, which is why we use these time-stepping methods instead, which are especially nice if A is sparse. Okay, now, for the system of ODEs itself, say the solution is stable if the real part of any eigenvalue of A is negative. So I should fix my notation here. And we're assuming that A is n by n. So all the eigenvalues from 1 to n must have a real part that is negative. That's important because that means we have exponential decay in the exact solution, which is consistent with how physical phenomena normally behave. Certainly, if you have a system that exhibits exponential growth, that's a big problem physically. Okay. Now, because this guarantees that the absolute value of e to the eigenvalue times t is less than 1. So a solution will decrease in magnitude over time. Okay. Now, this is how the exact solution behaves. So if we're going to solve the system by some kind of time-stepping method, we want to make sure that for our approximate, all these time-stepping methods effectively approximate to matrix exponential. So we want to make sure that numerical solutions have this kind of behavior also. Okay. So we're going to look at the two simplest time-stepping methods. So for explicit Euler, that is yn plus 1 equals yn plus delta t a yn. Now, since this is a linear system of ODEs, so time derivative is just this matrix spectrum multiplication. So I could actually factor a yn out to the right with I plus delta t a yn. And this is approximation of e to the a delta t. In fact, it's the first two terms of the Taylor expansion of e to the a delta t centered around t equals 0. Which makes sense because Euler's method is certainly consistent with the underlying ODE. Now, now I'm going to use letter M to refer to this matrix. So M is my approximation of e to the a delta t. So to be explicit, I'm not intended, I swear. Okay. Now, to make sure we have the same kind of behavior as the exact solution, so we require that the eigenvalues of M have absolute value less than 1 for a numerical solution to be stable. So this is based on this condition that the eigenvalues of the exact solution matrix are less than 1 in magnitude. So we require that for the approximate solution matrix. Dang it. Okay. Now, the eigenvalues of M are equal to 1 plus delta t times the eigenvalues of A. So for these to be less than 1, that means that if I were to draw a complex plane and I have a disk of radius 1 that is centered, that is centered at -1, and it has a radius of 1. So delta t times the eigenvalues of A must fall somewhere within this disk to have a distance of less than 1 from the center, which is -1. So that's a pretty severe constraint because the eigenvalues of A could get large, in which case delta t must be particularly small for it to, the whole product to fit within that disk. Now, if this comes from a system of ODEs, comes from a PDE, as you increase the spatial resolution, the eigenvalues of A spread out over a larger interval. So these eigenvalues get larger, thus forcing a time step to be even smaller. So this is a problem with a lot of time stepping methods, especially explicit ones like explicit Euler, that as you increase the spatial resolution, in other words, delta x is going to 0, delta t has to decrease with it. But that means you're taking more time steps, so you have much greater computational expense. In other words, most time stepping methods do not scale well to higher spatial resolution, which is a key theme of my own research area. Okay. So because of this constraint that delta t times lambda has to fit within this disk, so delta t has to be small enough for all these products to fit. Say that explicit Euler is conditionally stable. Yeah.
Yeah. So I'm wondering how we arrive at lambda I is equal to 1 plus delta t lambda I.
Oh, you have to n is equal to A. Because if you scale a matrix, you just scale by delta t, so you scale the eigenvalues. But then when you add a multiple of identity to the matrix, that shifts all the eigenvalues by that multiple. Yeah, so at least in this case, it's easy to express the eigenvalues of m in terms of A because m is such a simple function of A, but that's not always true generally. Well, oh, what was I thinking? No, I was thinking about something else. In general, if m is some function of A, lambda I of m is the same function applied to
Any function of eight.
yes. Yeah, where it's polynomial, exponential, even sine or cosine, yeah, any of that.
This case is just a minute.
Yeah.
And in any case, it's always be conditionally stable.
Explicit Euler is conditionally stable. Most time-stepping methods are conditionally stable. Remember? Now let's take a look at implicit Euler. All right, so implicit Euler is yn plus 1 applied to this system is equal to yn plus delta t a yn plus 1. Now, we'd like to express this method as yn plus 1 is equal to some matrix times yn. But to do that, so this time we need to do some rearranging. So take all terms involving yn plus 1 and move them to the left side. And leave yn on the right side. And I can still factor yn plus 1 out to the right, like I did with yn explicit case. So now, this is typical of implicit methods. I have to solve this system of linear equations where that's my coefficient matrix, and this is my right-hand side to get my new value, the solution at the new time. So another way of looking at it is I could say that yn plus 1 is equal to the inverse of that matrix times yn. So this right here is my m.
Is it equivalent to e to the power a to a delta t?
Well, let's actually, this is the next thing I'll point out. What's in the parentheses is the approximation of e to the minus a delta t. And then you take the inverse of that. So m as a whole is still approximation of e to the plus a delta t.
This is a dumb question, but I don't remember. So the x.
Well, okay, so the inverse of, just like with numbers, so the inverse of e to the a is e to the minus a.
I don't know why I was over. A is the matrix.
Okay, yep.
Just saw this in class yesterday.
All right, so now let's take a look at the eigenvalues of this matrix M. So lambda I of M equal to 1 over 1 minus delta t lambda I of A. Because the 1 over is because we're taking the inverse. And then for eigenvalues of the matrix inside the parentheses over there, we do the same as similar to what we have in the explicit case. But one point I need to bring back is that we're assuming here that the real parts of the eigenvalues of A are negative. But so then we're subtracting a negative. So what that means is the real parts of 1 minus delta t lambda I of A will be strictly greater than 1. And that's in the denominator. So the denominator is guaranteed to have a real part that is larger than the numerator. So we can conclude that the eigenvalues of m in absolute value are less than 1, no matter what delta t is. That's the key. So explicit Euler, delta t had to be small enough so that delta t times lambda I of A fit in that disk. We don't have a situation like that now. So we can say that implicit Euler is unconditionally stable. That's what we like to have, but very few methods have that property. And any that would have it are, if they're expressed as polynomial or rational functions of A, those are generally only going to be implicit methods that would have that property. So this is a big reason why we actually use implicit methods, because implicit methods we've seen can be a lot more work. I mean, we're solving a system of equations every time step. But because we can get away with using a larger value of delta t, I mean, not too large, we lose accuracy, but to at least maintain stability, have a qualitatively correct solution. It's easier to obtain that using an implicit method. Yes, it's more work per time step. We can take a lot fewer time steps. So the overall amount of work is less. And the expense of solving a system every time step isn't necessarily that bad. Like, suppose A came from like a finite difference approximation, then A would be sparse. Also, if you're using the same matrix, like a matrix doesn't change over time, you can do the LU factorization of this matrix once before you start time stepping, and then reuse those LU factors every time step, and save some expense that way. But implicit methods still have the same problem as explicit methods in that as you decrease the spatial resolution, this matrix identity minus delta CA becomes more ill-conditioned, and that can pose problems for instance, iterative methods for solving AX equals B. So for that reason, it may still be necessary to use a smaller time step. So implicit and explicit methods both have a problem of like if they come from PDEs and have their eigenvalues spread out over several orders of magnitude, which is what happens when you're coming from PDEs. So even if a method itself is unconditionally stable, you may still have a problem of computational expense increasing a lot as delta X gets smaller. All right. All right, so any questions about what we have here? All right, so I'm going to give you an example of a couple examples of some of the difficulties that you can have with time stepping. Okay. First, we'll look at a very simple system of ODEs. Y prime equals AY. For A, 2x2 matrix. B, 49. 49. So your initial data is 0. Now, the exact solution is e to the minus t 1 plus e to the minus 99t on minus 1. Okay. Now, this term is very small. E to the minus 99t goes to 0 very rapidly as t increases. So even for a relatively small t, you can approximate the solution fairly well by just including this term. But even though this term is quite small, it still causes a lot of difficulty for numerical methods applied to this system. Okay, so to give you an idea as to how bad it can be, if we're using explicit Euler, we have this condition that came about before. That the eigenvalues of A and delta t have to satisfy this condition. And in this case, the eigenvalues at 1 is equal to -1. And at 2 is equal to -99. So the two multiples of t that you see is the exact solution. Okay. So if I substitute both those eigenvalues into here, okay, and since the eigenvalues are real, that simplifies. We're not really worried about the complex plane. We have -1 less than 1 minus delta t is less than 1 from a first eigenvalue plugged in here. And for the other eigenvalue plugged in here, we have 1 less than 1 minus 99 delta t less than 1. Okay. All I did was I plugged each of these eigenvalues into here. And then expanded this, like this is greater than minus this and less than.
Yes.
Yeah, okay. All right. All right, now I'm gonna add 1 to all sides. Those. Two. Whoops. 2. Okay. So now if I solve for delta t, I get spin 2. That comes from this condition. But here I get delta t be positive and less than 2/99. So this is a more stringent condition. So this is the one that must be enforced. So I have to use a time step that's pretty small, so roughly like 0.02 or less. Otherwise, what will happen is my numerical solution, instead of exhibiting exponential decay, will exhibit growth.
Could you repeat the last sentence, the exhibiting growth?
Okay, so if delta t does not satisfy this, then my computed solution will grow over time instead of decaying like it's supposed to.
Only the second. Both conditions?
Well, if I violate this one, this is a more stringent, so I'm not really care about the other one.
There will be growth.
in the computed solution.
The solution grows, it will be unstable.
Yeah.
So, what happens if the eigenvalue has solely imaginary parts?
Oh, well, that'd be, but this condition still applies in a complex plane, so it's still going to cause a constraint on delta t. As I said, in this case, because the eigenvalues happen to be real, I was able to do this.
So it is assumed that it has
Um,
a real,
sorry, what?
it has to be, we have to assume that it's going to have a non-zero real.
Well, it doesn't matter.
Oh,
Whatever eigenvalues you have, real, imaginary, complex, for explicit Euler, you have to satisfy this. It's just that because the eigenvalues are real, I was able to do this to get a simpler condition. If the eigenvalues were complex, what I'd have to do is think of this as square root of real part squared plus imaginary part squared less than 1, and then use that to figure out which algebraically might be a pain.
I
Yeah.
remember that.
Okay.
It should be just take the Z.
Yeah.
I don't remember the word for it. You meant it.
Oh, yeah, but, well, here we're focusing on the absolute value.
Yeah.
Yeah.
I remember arguing,
Oh, yeah, but that's part of a complex number we don't care about here. Yeah,
as long as you know the equation.
yeah. Yeah, so regardless of real or imaginariness, this product cannot wander too far away from -1 in a complex plane.
I think I remember seeing one or I think Victor was there too. Do you remember from ODE class we looked at the imaginary values? Yeah, I think we did. I don't know which method it's.
Oh, okay, is this from 605? or-
So far, yes.
Yeah, but I guess that class didn't really get into the numerical methods probably.
No.
Okay, yeah. Yeah. Okay. All right. Now, here's an example that actually comes. First, I have questions about. All right, from a PDE. So it's clear interest to us. All right, so let's suppose we have PE UTT, so this UT equals UXX. And that leads to anticipation of this discrimination y prime equals AY, and the A in this case is 1 over delta X squared. So the familiar centered difference for a second derivative. Okay. Now, the eigenvalues of A, and there's a formula for them, but we need to know here for this example that the spectral radius of A, which is the maximum absolute value of any eigenvalue of A, is less than 4 over delta X squared. So that's what we use as our estimate of the largest eigenvalue. Now the matrix is symmetric, so the eigenvalues are all real. So explicit Euler again is stable if, so the same condition before, 1 minus delta t 4 over delta x squared is less than 1. Okay. Now, so if we real eigenvalues, we focus on an interval on a real line. Okay, then I'll add 1 to all sides. So this inequality just means that delta t has to be positive. This inequality, this being greater than 0, is of more interest. So we get delta t must be less than delta x squared over 2 for stability. Oh, for some reason I have less than or equal to in those. It should be strictly less than. Okay. Yeah.
What is delta x squared?
What?
What is delta x squared?
Well, delta x is we're going from a PDE, so you have a spatial resolution and a temporal resolution. So delta x is a grid spacing in x.
Grid space.
I guess before we got on time stepping, it was normally referred to as h.
Yes, okay. 1 over, yeah, I remember the matrix, 1 over x squared.
Yeah. Okay. But now that we have both space and time, we can't use h anymore. Some authors, including my first advisor, when dealing with problems involving both space and time, would use h and k, like h for space and k for time, but that just seemed too weird. So, let's do delta t, delta x. So that's a pretty severe time step restriction. So for instance, if you double, or if you cut the spatial resolution in half, so you're doubling the number of grid points, that means you have to decrease delta t by a factor of 4. So this is pretty bad, actually, because that's going to cause the computational expense to increase rapidly as you use a finer spatial resolution, because of that quadratic dependence of delta t on delta x. So explicit Euler is not really a good choice for solving a heat equation because you must take time steps that are so small.
So it should be.
So that's why people like to use implicit methods for a problem like this. Now we could use implicit Euler, and that'll be unconditionally stable. But I want to highlight another implicit method. Called the Crank-Nicolson method. What?
We've never heard this.
Oh, yeah, I haven't brought it up here. Now, I have brought up a time stepping method similar to this. Is actually the trapezoidal method. So the way it works is, so y n plus 1 equal to yn plus delta t over 2 a yn plus a yn plus 1. So you have yn plus 1 on both sides, so that's what makes it an implicit method. I apologize, but I realize I'm falling behind. I need to speed it. So welcome to hold questions until after. If I rearrange this, move all yn plus 1 terms to the left side and factor as much as I can. Then I get this. I'm solving a system of equations. So I have identity plus delta TA over 2 yn. That forms my right-hand side. And I'm solving a system where this is a matrix to get, so identity minus delta T over 2a, get my yn plus 1. So that means my m, so yn plus 1 equals myn, where m is the inverse of this times this. Matrix has multiplying yn just by moving this over to the other side. So then the eigenvalues m are 1 plus delta t over 2, eigenvalue of a, 1 minus delta t over 2. And because we're still assuming that the eigenvalues of A have a negative real part, the real part of this is guaranteed to be larger than the real part of this. So this is actually guaranteed less than 1. It is unconditionally stable, like implicit Euler is. But as delta t gets larger and larger, if you look at the focus on the larger eigenvalues of A, the ones here become negligibly small by comparison. So as delta t goes to infinity, the eigenvalues of m converge to -1 because of this opposite signs in a fraction. And that's not good because that means the solution is going to bounce back and forth. It's going to exhibit non-physical behavior. So even though we could get away with a large time step, just to make sure the solution remains bounded, it's still going to exhibit screwy behavior if we choose it to be too large. So be careful about that. But it's still nothing that a lot of people like to use because, like implicit Euler, it is unconditionally stable, but one pro it has over implicit Euler. Implicit Euler is first order accurate, but Frank Nicholson is second order. Are any questions about? Okay. All right, so that's all I'll say about stability here. But now there's one other. So there's one nice approach to analyzing stability. This actually comes up in the last homework. and these are relatively simple schemes, called von Neumann stability analysis. So it's a nice way to determine whether a numerical scheme is stable, or under what circumstances it's stable. Okay. So the problem, there's going to be some examples of this. The PDE is UT is equal to some constant D times UXX. And the initial data is e to the I kx, where k is some constant. So in that case, the exact solution turns out to be e to the minus d k squared t e to the I kx. So your solution, the exact solution is a multiple of your initial data. It's multiplied by e to the minus d k squared t. So this is labeled capital G of k, and it's called a growth factor. And we need this growth factor in absolute value to be less than or equal to 1. Now, the exact solution is certainly going to have a growth factor that's less than or equal to 1. And because the constant d is assumed to be positive, that's what we require for heat equation, to have a stable solution. So the idea behind von Neumann stability analysis is you substitute your solution at time Tn to be e to the I kx, the same initial data that we have here. And then you find your growth factor, which is your solution at the new time divided by your solution at the old time. Because the idea is your new solution is equal to your old solution times your growth factor. And we're going to require, as for the exact solution, that the growth factor be less than or equal to 1 absolute value to ensure stability. Okay. Yeah.
The growth factor is only the first term.
Wait, it's only this part. Yeah. Yeah.
Just the first.
Yeah, so it's what's multiplying e to the I kx. Right, well, now I'm going to show you. So we're going to use explicit Euler in time, and then center difference in space. So UJN is our approximation to U of XJTN. So subscript is corresponds to an X value. Superscript corresponds to a T value. Whoops, forgot the N here. So what you do is, okay. So now what I'm can rearrange this to solve for what the new value we're computing, UJN plus 1. That's equal to okay, UJN plus R times plus 1n minus 2UJN plus UJ plus 1n, where R is d delta t over delta x squared, just condensing all of those constant factors. Okay. Okay. Now, if I let UJN equal EBIKX, then that means that UJN plus 1 is equal to G EBIKX, whatever growth factor G is, which we don't know yet. Also, UJ plus 1N is equal to e to the I k x plus delta x. So that's e to the I k x UJN. And similarly, UJ minus 1N is e to the minus IK, oh, whoops, sorry, e to the IK delta x, sorry. And then J minus 1N is e to the minus IK delta x UJN. So now I can make all of these substitutions. So in fact, everything here is a multiple of UJN. So I make all of these substitutions in here. So once I simplify, since UJN is a common factor in every term, I'll just cancel it. And then that gives me an equation for G. So my growth factor, which depends on K, but I'll write it as G, is simplifies to 1 minus 2R times 1 minus cosine K delta X. All right, what?
So we're just substituting this, right?
Yeah. Everything you see here, UJN, UJN, one, all of these are substituted.
This one is this, so that cancels out to the left. Okay, then.
Yeah.
Minus 2 plus. Okay.
Yeah. Yeah, and then those two complex exponentials combine to make a cosine.
Mhm.
And there's more details in the notes. So, okay, that's far. Okay.
So 2. K delta.
So this whole thing has to be less than or equal to 1 in absolute value. But for that to happen, and the thing is, so we need G less than or equal to 1 for all K. So regardless of the value of K, That means that R times 1 minus cosine k delta x must be less than or equal to 1. But that's the same as R times, so using a half angle identity, the 1 minus cosine is the same as 2 sine squared k delta x over 2 must be less than or equal to 1. Okay, but of course the sign is at most 1. So if we take the worst case, that means that R must be less than or equal to 1/2. So d delta t over delta x squared must be less than or equal to 1/2. So this right here, that's squeezed in the bottom, is the stability condition when you're using explicit Euler for time stepping, which is consistent with what we saw earlier, and the center differencing in space. So certainly it's conditionally stable, but we already knew that.
Are we expecting this kind of problem in exams? So if you give us an example like that and we have to figure out the condition for stability?
No. Yeah, I don't want I don't want that to get to algebra E. So yeah. I mean, it's possible I might have to work through certain things, but that wasn't going to be one of them. The general idea behind fundamental stability analysis and what you're trying to find out by doing it, that's something that I could ask about.
The one good thing about stability analysis is you know the goal.
Yes. Yeah. And I think it's depending on the scheme, who knows how bad the algebra might get, or if you got to use trig identities or whatever. Okay. I'm gonna do one more example. Okay, but yeah, for more details about the algebra in the notes, so I encourage you to look at that. I apologize for the rush, but I have a lot to cover on Thursday also. And so this to spill over into that. Because what I cover Thursday is really all about the 4th homework. Okay, I think we're dealing with the same problem. Yeah, okay, same problem. So a shortcut approach, which I kind of hinted at in what I just did, is just set UJN plus 1 equal to G, UJN equal to 1. UJ plus 1 to n is e to the I theta. UJ minus 1n is e to the minus I theta, where theta is k delta x. This just takes into account that UJN is going to cancel out anyway, so we'll just go ahead and substitute this instead. So it's not really that much of a shortcut, but okay. Okay. So the method I'm going to apply this to is Frank-Nicolson. So we have uj n plus 1 minus uj n over delta p is e over 2. And then we have center difference so this is uxx at time n to tn, and then I also have that at time n plus 1. Okay. I just realized in my shortcutting, I did not cover everything you see on this side. Yeah, so but we cobble together. So uj plus 1 n is the same as ujn, except we got to multiply by g. But anytime you're at time tn plus 1, you have to include a g. And uj minus 1 n plus 1 is g e to the minus I theta. Oh, dang, I'm running out of time. I gotta substitute everything. T 2 theta minus 2 plus minus theta squared plus g del theta minus 2 plus e minus I theta squared. Yeah, so what do you get from this uxx and this uxx are exactly the same, except the second one's multiplied by g. Okay. All right. Now, all right, so then we try to simplify and get isolate g. So g is equal to 1 plus r, where r is once again d delta t over delta x squared. And you get g plus 1 because we have a g here but not there. And everything simplifies to cosine theta minus 1. But now we have g on both sides of the equation. So what I need to do is I need to multiply this out and take all terms involving g and move them to the left side. So then I can isolate g. And what we get is 1 minus r, 1 minus cosine, over 1 plus r, 1 minus cosine. Okay. If I do the same trig identity thing as last example, 1 minus 2r sine squared theta over 2 over 1 plus 2r sine squared theta over 2. And that's guaranteed to be lesser equal one, it adds some value anyway. I should emphasize that, that's all we need. Just because the denominator is gonna be larger than the numerator. By using that trig identity to sign square, that makes it clear that the denominator is always gonna be positive. So, oh, this is totally written wrong. Signs, not sure why we wrote differently top versus bottom. Okay. Okay, there is one part of one problem in homework 4 that calls for carrying out a one-one visibility analysis. I have another example in the notes that I don't have time for, but it's a 2D example, so the homework is 1D, so. Okay. But yeah, it really is, you make substitutions, do whatever algebra or trig is called for to isolate G, and then find out when it's less than or equal to 1. Okay. So all that's left is finding different schemes for a simple one-way wave equation, which is the subject of 4 homework, and that'll be Thursday. So I rushed through things. Again, I encourage you to look at the notes, and it's all there.
No, it should be using it.
Okay. Alrighty. Till then, 1 clap to go.